Hello, in this video I want to talk about interesting Haskell abstraction. I come to it after this question on Stack Overflow. What I need here, I need to implement function which adds an element once to every list of a list. So if I have such a list of lists, for example, I want to add 7 at every list only once. So I have the first list here. Then somehow modify the first element of this list, the add 7, and then the add 7 at the second element, and at the third at last. So I start from this solution, but then some answers was the much more nice solutions, and I take this. And also this is a very interesting answer. So let's just take this implementation and put it here. So but I want to generalize this function. Here this function, it's take some element e and add it to the first element and add this new list to the tail of excess, and then it add all this list to the mapped tail of this list. So it can be done with the recursion. But here I want to change this signature to this signature. I want to generalize. Actually, we have a list of A's here, and we do the modification of these A's. So the modifications, we can do this with function from A to A. Okay? Let's call this function. Let's comment this type signature and use this type signature. I will call this function g, and this function g is applied to x, and then they pass this function recursively. Okay. So like this. Actually, I come to this signature after I read this answer. It is very interesting. So okay, and this name was also helpful. Okay. Now let's reload the module and try to run this function. Okay, for example, if I have some list of 1, 2, and 3, and I want to add 1 to every element of this list and get all the possible versions of this adding. So we can see here I take a list of lists there. Each modification applied to every element, and they collect all versions, all the modifications of elements. So it's somehow like map, but map, what maps do? It take a list and it modifies every element of the list. But this thing is modify on each element only once, and other elements stay the same. So it's like a mutation somehow from only one property of the object. So I think this is very interesting, and we can make a type class of this. Okay, let's do it. Class, I will call it Eachable. From some type E, and we have this function each that takes some function from A to A, and it takes some E with A and produce a list of E with A. So E is type of kind star to star, and it's embeds some type A which we modify, and we somehow produce different versions of this container, modifying every element only once. So now we can instantiate this for list. Each of no matter function empty list is empty list, and each if they have some function g, and let's unpattern match the an empty list, then they actually need this implementation. They can use it here. Of course, I must change the recursion. And let's comment this thing. Now every list is eachable, okay, and they can use the each again. Each plus one some list. Okay. And not only a list can be eachable. So we can make, for example, a tree eachable if you want to modify it only in every node, but stay other nodes unmodified and get the all possible versions of this modification. Let's implement this thing for a tree. So we define a tree like this. It's either empty tree or the node which have some left tree, some element, and right tree. Okay, and let's derive show. And now we need to make an instance of Eachable. Instance Eachable tree. Okay. If they each on empty tree, no matter with function, with which function, we receive an empty list of trees. But if they do this with some function g on not empty tree, they need this tree, and the unpattern match also it here. And here we need to think how can they build this tree. Actually we need to build a list of trees where every element is only changed once. So the number of trees in this list will be equal to number of elements in my tree. So if I somehow can to enumerate my tree elements in some of the tree traversal order, left, right, or in order, pre-order, in order, or post order. If I do this, then every node will have an unique number, so increasingly one by one. And after this, if I go through a tree with some order traversal, and also during this working I will carry some counter which will be incremented on every step. And if I will start from 1 at the root, and if our counter is equal to the node index, this then means that at this point they need to modify this node only once, and all our subtrees we need to skip the same. So this is the main idea, and let's try to implement this. First of all, we need some helper function for this, and this function I will call it count. It will count the number of nodes in the tree. So count. If we count the empty tree, then we have 0 nodes. If we count not empty tree with some node L, left subtree L, and no matter which element we have here, and we have right subtree, then the count is equal to 1 plus, so we count this node and plus, then we go to recursion, count left and count right. Okay. And next we need to, let's build some tree here and try to count it. So if we have tree which contains some element, for example 2, and some left and right subtrees. Okay, here we have node empty, 1 empty. So this is a simple tree, and also the same tree here. Same tree here with 3. Okay, let's roll on this. Count empty. So I have some error here. I have so let's undefined. Let's do it undefined. Oh. And now let's look at our tree. We have it and we can count it, okay? We have 3 nodes here. Okay. The next thing, how can we modify this? So we need to start from, actually we can take all the numbers from 1 to count all the nodes in the tree. And from which this number, like a seed, we can So we have this number and we have the tree. And this is all what we need to find our modified then our node which we need to modify. We will use counter for this. So I will use fmap here and some lambda which take this index, and it calls some helper function with our function g which do modification, and then we pass counter. We start from 1. When we pass our index of the node, which we count from 1 to n, every node has its index, and then we pass our tree. So now I need to define this help e function. So this help e function works like this. It takes some params. No matter if they have empty tree, they will return an empty tree. But if they have not empty tree, they have a tree with some modifier g, with some counter c which start from 1 at the root, and they have some index I which tell us in which node they need to do the modification g, and they have not empty node. So we need to reconstruct this node with some L prime, A prime, and R prime. There. And now we need to define these primes. I will start from A prime. A prime. This is the node, and we modify this node with our GA, with our modifier G function from A to A. We modify it if our counter C is equal to our index. Okay? Then we do this modification. Otherwise, we just skip our node and we state as it is as A. So next thing I need to define L prime. So if our counter is equal to this node, this to our index I, this means that we found our node, only one node to modify, and we can stay our left tree as it is. Otherwise, we need to search in our left subtree with function modifier g and counter c plus 1, and the search for index I in our left subtree. Okay. And the last prime for R. It's a little difficult than L. Also, if our counter is equal to I, this means that we do our job, we modify this, and the right subtree stay as it is. And otherwise, we need to call our E function again with G, but the C here, what the C here? Actually, to get the correct number here, we need to think about how we enumerate our nodes. So the counter here is the counter of C plus plus the number of nodes in the left sub-branch of this tree. So and then plus 1. So we take C, we take count number of nodes of left subtree, and we also do plus 1. So this is the correct count of this node, of the count of the root node of the right subtree. Okay. And also we need to pass our searchable index and right subtree. Okay. And I think this is correct implementation and it should work. Let's try to reload this. Okay. As always. Of course I need to take a tree here, not 10. Let's reload and we're done with this. And so let's try to run our each function, polymorphic in each function on our tree tr, and we want to modify every node plus 1. So you can see that we have this all possible version of subtrees. Here they have first tree modified at the root, our 2 increase plus 1. The next tree here, they modify the root stay the same, the right stay the same, and the left modified. And then we modified the right node. Okay. What we can do next? Next thing we can do, I provide one more example. What if we have some type which describes some animal, which have some parameters a, and it defined like this. It have some speed of type a, it have some size of type a, and it have some smart parameter of type a, how smart this animal, and the deriving shows this. Now we can do our animal with instance of our Eachable animal. We need to define each function for this, which takes some modifier. It takes some animal with params sp, sz, and sm, and we need to do the list of all the mutations of this animal. So the first animal is mutating in its speed. So G is mutator, and in this mutator is mutated speed, and so on. So let's copy this from here. And we mutate every parameter. Okay, now we can try to use our each for animals. What if we have some animal and we want to increase a speed plus 1 for every parameter of this animal? The animal will be animal will 1 1 1. Okay, so let's do it in our Gesh CI. And here you can see that I take this one animal, this started parameters, and I mutate it to 3 animals. And every of these animals is different from each other in one parameter. So now we can take a list of this and map it again with our each function, which in the second phase mutate our animals. And we can see that here we mutate again every animal, and we can do this so on and on, and this is will grow like a tree. Okay, the animal mutate in all possible ways, and then we can pick up some funny animals and somehow collect them. Okay, so I think this is a very interesting abstraction, and it was very funny. So guys, thanks for watching. Push like button, push subscribe, will write the comments, and see you in the next video. Bye.